Hello everyone. Today my topic is hardware implementation of an artificial neural network. My name is Pawan Chauhan and my ID is 21C018. Let's start. The topics that we will discuss today are the introduction, implementation, test and results, and finally the conclusion. Let's start with the introduction. Most authors have shown that the solutions with artificial neural networks reach better results in the implementation phase with specific hardware. That means that we have to use a specific type of hardware with specific, um, what we can say, requirements, such as a PC or a workstation. The existence of these solutions in hardware is of extraordinary importance for areas such as applied sciences and health science, as its simplest way to see that where we need not basic but complex calculations or something is riding on the stake, we need to have precise answers for that. So it comes in play there. The artificial neural networks are parallel distributed systems since they can receive several inputs simultaneously and distribute them organizationally. With this architecture, the information stored and shared in all the processing units of the neural network improves the performance and reliability of the system implemented. The hardware is basically dependent on the number of inputs and neurons, which is the connection with them, and the number of that greatly increases or decreases the accuracy of the system. The next slide. Now we will move forward to the implementation. The implementation of the artificial neural network has become a part of many scientific projects. There are specific projects dedicated to the solution of a complex problem that in principle would be insoluble. First we will talk about the hardware platform which we will be using in this implementation. The hardware chosen for this was an FGPA with an embedded microblaze. That's a name of the microprocessor. It's a microprocessor with greater flexibility, greater performance, and low consumption of energy. And to add more to that, it works on the RISC architecture, which is the reduced instruction set computer, so that we can feed great inputs and get many outputs on even a low hardware compatibility. This microprocessor is soft core, which is it only has a set of features configured with the hardware description language, which is the language used. It was selected because easy to use, area efficient, optimized, cost effective, and the number of embedded system depends exclusively on the capacity of the FGPA. Moving towards the next. Here is the exact architecture of the hardware we are going to use. As you can see, there is the data side, there's the ALU, the cache, register, decoding unit, instruction buffer, cache memory, special purpose registers. The type of neural network used in this project was feed forward neural network. That is a network that allows only connections in the input towards the output direction. This option results in more considerable spreading at the level of the development tools that will enable the fast implementation of models. You can understand it like holding a torch. You have a single source and many destinations. It works like that. The code program for this neural network was developed to be general to eliminate the possibilities of OS not being able to support this. The network would have to receive a variable number of inputs and neurons, which is the connections. The number of neurons in the hidden layers allows us to adjust the size of the network to the complexity of the system being used. So next is for internal calculations of the activation function, the hyperbolic tangent function was used. This function supplies non-linearity to the neural network, which eliminates the simple working of the system. So however, to make the processing of the network in the hardware faster, the function was used in the reduced form, which is the second image. The process was implemented as stated in expression 2.2. The advantage is evident since it only has one exponential function rather than the 4 in the first image. In the output layer, the linear function of the expression was used was 2.3, which is this one, right? So the expressions below, y represents the output and x represents the input. So next we will see the test cases or the tests. So as I explained earlier, it was somewhat like holding a torch. So each input is the source and then it communicates with the output. So the several test cases were performed with artificial neural networks implementation. The tests were used to verify the correct operation of the network, modifying the size of the system and comparing the results with one obtained with the implementation in MATLAB. So let's move further. So the conclusion of this whole would be, this work allowed us to verify essential aspects regarding the hardware and software implementation, the potential of the hardware chosen for implementation, and after all, we only used 33% of the resources offered by that FGPA. The developed system was tested with different models of neural networks and using data from a real plan. The tests were made possible to verify the performance of network. Although this type of implementation was slower than a usual implementation of artificial neural network using a PC, but a FGPA board is less expensive, more user friendly, more cost friendly, less power consumption, and main is it does not depend on an operating system. So that was all for me. Thank you.